All right, just take a second and look around you. I mean, really look. The screen you're staring at right now, the chair you're in, your desk. How in the world does all of that stuff out there get, well, in here, inside your head? You know, it kind of feels like magic, doesn't it? But it's not. It's actually a secret code, one that's carried by light. And today, we're going to crack that code together.
Okay, so let's get personal with it. Right this very second, how are you seeing this screen? It feels totally instant, right? But what you're actually experiencing is the starting line of a pretty incredible journey in physics.
So here's rule number 1 of that journey. Light is basically a messenger, and it's a messenger that never ever gets lost. It travels in a perfectly straight line from whatever you're looking at directly into your eyes. No detours, no scenic routes, just a direct pipeline of information.
Now, to keep track of this journey, we need some kind of map, and luckily, scientists came up with a super simple tool for that. It's called a ray, and really, it's just an arrow that points in the exact direction the light is moving. For the rest of this explainer, these little arrows are going to be our guide.
Okay, so we've got our light ray shooting along in a straight line until, bam, it hits something. Could be a wall, a window, your t-shirt, anything. And at that exact moment of impact, that ray of light has a choice to make. It's facing one of 3 possible fates.
First up, we've got reflection. The easiest way to think about this one is to imagine light is like a super bouncy ball. It hits a surface and just ricochets off in a totally new direction. Now you're going to want to keep this one in your back pocket because it's the absolute key to how we see pretty much everything.
Fate number 2 is absorption. So instead of bouncing off, the light just gets, well, soaked up by the object. But that energy doesn't just vanish into thin air. Nope, it gets turned into heat. You ever wonder why wearing a black t-shirt on a sunny day feels so hot? It's because that black fabric is absorbing a ton of light energy and turning it into heat.
And that brings us to our third and final fate, transmission. This happens when an object is basically an open door for light. The ray hits it, says thanks, and just passes right on through, continuing its journey on the other side. A perfectly clean window is the classic example here.
Okay, now here's where things get really cool. Those 3 fates we just talked about, reflection, absorption, and transmission, they're not just abstract ideas. They're actually the very things that define every single object in the world around us.
And this all leads us to 3 words you probably already know: transparent, translucent, and opaque. What category an object falls into is decided entirely by which of those 3 fates it picks for the light that hits it.
Let's connect the dots here. A transparent object, like a piece of glass, it chooses transmission, letting all that light pass right through so you can see clearly. A translucent object, say frosted glass, also chooses transmission, but it kind of scrambles the light on the way through, so things look blurry. And then you have an opaque object, like a wooden door. It just slams the door shut on transmission, choosing to either absorb or reflect that light instead. You can't see through it at all.
All right, let's zoom in a bit. We're going to put absorption and transmission to the side for a minute and focus completely on reflection. Why? Well, because for almost every solid thing you see, your desk, your phone, even the face of a friend, reflection is the whole reason you can see it in the first place. So when you look at something, what you're really seeing is the light that has bounced off of it. But here's the kicker. This bounce isn't random. Not at all. It follows a super precise, totally predictable rule. So, what's the secret to this perfect bounce?
To figure out the rule, we need a starting point, a reference. So scientists came up with this imaginary tool called the normal line. Just picture a line sticking straight out from the surface, at a perfect 90-degree angle, right at the spot where the light hits. This is the ruler we're going to use to measure the bounce.
So let's imagine we use our new ruler to measure the angle of the incoming light ray. And let's say it hits at exactly 45 degrees. Well, what scientists discovered, and this is so cool, is that the outgoing ray, the bounce, will always leave at the exact same angle, 45 degrees. It's a perfect mirror image of its approach, every single time. This isn't just a coincidence. It's a fundamental law of the universe.
And there it is. That's the secret code we've been hunting for. It's called the law of reflection. It's so simple, it's beautiful. The angle that the light comes in at, what we call the angle of incidence, is always equal to the angle that it leaves at, the angle of reflection. Simple, elegant, and it's the rule every time.
You know, what's so amazing about a universal law like this is that we can boil it all down to an incredibly simple, yet incredibly powerful little bit of math. A formula that packs that entire rule into just a few symbols.
And here it is, in all its glorious simplicity. Ready? Theta I equals theta r. Now, don't let the Greek letters scare you. Theta is just the symbol scientists use for angle. So this formula literally just says, the incoming angle equals the outgoing angle. That's it. That tiny little piece of code is the master key. It governs everything from your reflection in a puddle to how we build the most powerful telescopes in the world.
So the next time you look in a mirror, remember that elegant little rule, theta I equals theta r. That simple bit of code isn't just letting you see yourself. It's powerful enough to let us build giant space telescopes that can see across the entire universe. And it kind of makes you wonder, doesn't it? What other cosmic secrets are just hiding in plain sight in the simple rules of the world all around us?